concept called model-driven engineering, and the reason the talk is called Back to the Future is it's quite an old concept. So here's a book from 2003 by OMG Press, and it's aptly named because you look inside and you just think, oh my God, this is awful. But actually, I think model-driven engineering is sort of an underutilized form of development that could have quite a rich future. So who am I? So I'm a tech lead and engineering manager for what we call an information engineering team at JP Morgan. So our team's primary responsibility is delivering things like code generation according to data models for developers to use across the bank. I spent 5 years at Goldman, and then I've had 6 years at JP Morgan, and I've had roles across different teams in investment banks. So front office, sales and trading, back office, finance, regulatory reporting, and then where I'm at the moment, core engineering and architecture. And 2 years into my Scala journey, so the information engineering team use Scala heavily because it lends itself to sort of the domain that we're working in. So that's the problem. This is my favorite picture, like that I've come across in sort of computing and like my career, because it just highlights what we're dealing with in large organizations. So what this is some poor soul has drawn a representation of what happens with a mortgage in a retail bank. So you got like the customer on the bottom left, and then sort of the mortgage is originated, and then it just goes everywhere. So you can see the number of nodes, and a node could be a system, a particular manual process, whatever it is, right? A database. So highly complicated. How many times has someone typed class mortgage into an MD into an IDE, right? How many times is this mortgage, modeled, and how many times do we lose data or get data incorrect across this system? It's a big problem. So really, it's just highlighting organizational complexity. So, in a large organization like a bank, we're not starting from scratch. And actually, a lot of the work that we do in financial organizations is technically quite simple. It's rare to have very technically hard problems. You might have that kind of thing with high frequency trading, or quants may do stuff with graphics cards and stuff, mathematically complex problems. But the majority of problems we deal with are functionally complex, and really we're siloed organizations. So the problem is that structure means things quickly descend into a swamp of functional complexity. We have long-lived business processes. So like, Google can just decide to turn off Google Plus, and that's it. That's the end. Goodbye. You don't have to maintain that anymore. But we can't just switch off stuff. We have to maintain these long-lived processes. And therefore, you get, diverse infrastructure. You still have mainframes lying around doing their thing. You got bare metals, VMs, private cloud, public cloud, a mix of those things in some cases within the same team. You got a wide range of programming languages, databases, anything you can think of we're using. And of course, manual processes that haven't been systemized. So, organizations like banks, we run lean typically. So that results in people like quants or traders systemizing things in Excel, and tech, trying to play catch up. So, I think Conway's law applies in large organizations, and it's very difficult to manage large projects where you have to have changes across the bank. So all that results in really sort of ubiquitous physical transfers in an ad hoc way. So you can't track data lineage. You don't know where the data is going once it's originated. There's no real design traceability, so we don't know how many times a particular data concept, like a mortgage or an account or a client, is modeled in the various systems, and consequently you have high costs of change, because actually a small change that you think is trivial can actually result in a large change, the butterfly effect of changes across the bank. That's very hard to manage. Data quality obviously suffers in that environment, and things like developing centralized entitlement systems and things like that, it's very hard. So the question there is like, okay, is that just a problem for large companies like JP Morgan? If I have a startup, do you have, presumably it's all fine, right? Well, no. So Monzo is obviously a challenger bank in London. They have 8 products I counted on their websites, and they've resulted in 1,600 microservices to support 8 financial products. JP Morgan, we have thousands and thousands and thousands of products across different lines of business. So because finance is like a very, very complicated domain, you quickly get mired in this swamp of functional complexity. However, from the literature I've read, they have said, there's a shared core library with these microservices where things like rewriting core abstractions and marshalling of data are handled. So I think they get the problem. And actually, what they've said here indicates that they are doing some form of model-driven development. They're agreeing on standards. They're agreeing on how data is transferred over the wire. So I think they're on a good path there. But it's just to highlight that depending on the size of your organization or the domain that you're working in, you may not be a large organization, but you may be working in a domain that's very complicated. You're going to start to have problems when you scale up and have lots of different systems trying to talk to one another. Okay. So what is model-driven engineering? Well, really the focus is on the creation of domain models in a sort of domain-driven design fashion, right? With the ultimate goal of increasing compatibility between systems. The standard around this really was defined quite a long time ago by OMG, so the Object Management Group, who sort of took over UML. But you don't need to sort of use that, right? And organizations like Microsoft and Amazon and so on use something called TLA Plus, which is formal methods for agreeing on what the interface should be in distributed systems, like the interface between different parts of that system. So I think that's a good thing to do if you've got the time and the budget to do it. But I'm not advocating for that in this talk. But I think what I am advocating for is a more formal approach to specifying a domain model and to share that representation of that model with others, right? And when we talk about models, we've got three main sort of categories. So we've got a conceptual model. So we need to agree on what an account is at a conceptual level. And then typically there's a logical representation of that. So that would be stuff we write in an IDE. So in Scala, our traits and case classes, right, to represent that data. And then you've got the physical. So that's, what the data at rest. So, or, it might be a data on the wire in the form of some sort of serialization library. And obviously there's a lot more kinds of physical model than there are logical typically. So we're interested in modeling both logical and physical to some degree. So UML, that's usually like, when people come across like the Wikipedia page for model-driven architecture or engineering, like it'll quickly reference UML, your eyes glaze over, goodbye, no thank you, right? And UML is really, really complicated. And there are some extremely sophisticated and difficult to use tools to author UML diagrams. We call them case tools, and Magic Draw, Erwin, there are others. And really, like for the very, very large models, that where it's hard to fit in your head when you're writing it in a textual way, UML is probably still the only game in town for architects. Not actually, a lot of architects are not programmers in corporations. So UML is still used, And there are what we call executable UML, so things that convert UML into useful code, DDLs and stuff, but there's really no standardization there at all, right? It's different between the different tools, what the output you're going to get, there's no agreement. And the different tools will have their own representation of UML. They won't all have the same model underneath of what UML is. So, if you're starting model-driven engineering from scratch, I would suggest maybe not using UML as your starting point, but that's a controversial opinion. And of course, once you have some diagrams or a model in some textual language, or if you have done a diagram, fine. Those diagrams or models they don't really serve any purpose, right? So we actually need to transform, go from a model representation to actual code, system text, right? So we call that, model to text transformations. You can also do model to model transformations where you say, you got a very large model, you're only interested in part of it, so I'll filter it and then generate a new model from that. So yeah, those two forms of transformation. But really, that's sort of nuts and bolts of model-driven engineering. Where if you're delivering a service that does model-driven engineering, and supports that process, then it's all about the transformations, going from some abstract representation to something concrete that you can use in actual systems. And that's what we spend a lot of time doing in my team at JP. So things like UML, other modeling languages, what they have some structure underneath, and we call that a meta model. So a model of a model, in the same way that metadata is data about data, right? So when we're working in integrated development environments, we typically this third level M1. So we're writing classes. Here we've got person. Person has an employment type and a date and a name, and it inherits from some party interface, right? And then we create instances of it at runtime, right, which is the model instance layer at the bottom. In a meta model, we operate a level above that. So we say, okay, well, how do you model a class? What does the class have in it? Well, the class has some attributes, right? Those attributes have a name and they have a type. Okay, so how do we represent the inheritance there? Well, we'd say that's a form of relationship, or a generalization is the general parts that we use. And okay, so what are these things? Well, they're all instances of something that at the top, which is sort of our God object, in this case called element, but you could call it entity, whatever you like. But yeah, so these, three things. So you have a relationship, you have something that represents some form of classifier, could be an interface, could be anything, right? You have different types of classifiers, and then some kind of attributes, or you might have operations derived from attributes. So it's really like, how do you model a model, modeling language, right? Is what we're dealing with. And then, okay, you want to take instances of that meta model, store them, and do your transformations, so you can actually end up with useful code. So this is like a very high level code generation process that you would probably find defined in this book somewhere. And we've deployed a version of this at JP Morgan. So you can start with your model, so in this case person, and then you ingest that. You ingest that into your you write that into your meta model representation, and then store it somehow. There's different ways of storing it. You can break it down into its constituent parts, or you can just store a serialized version of it. It depends what you want to do. And then you would need to write some transformations. So something that's going to take things like classifier, attribute, other things in your meta model, and actually convert that into code, and then place that into repositories like Maven or PyPy. And then this there for developers to use, right? So they can take your generated code as a library, and then send and receive instances over the wire between applications. So that's really what we're talking about in terms of model-driven engineering. So you start with some kind of model, you generate code from it, and you use it. and then you can iterate on that process. So some people will sort of see that and say, well, does that slow you down? I think not necessarily. It could actually speed you up, because when you agree on the model and you get generated code from it, you don't have to rewrite the same thing over and over again in your different systems. And you can support things like TypeScript generation if you wanted to integrate between your UI server or your UI and your microservices, for example. So you can actually save time in some ways. Well, obviously there's overhead in setting all this up. Obviously the serialization is important as well. So typically we wouldn't just co-generate the classes. We'd want to co-generate some way of serializing those in different formats that we can send over the wire via message bus or over the web or even file-based, right? So we'd want to support that as well. Things you can do with the meta model. So you can track changes between versions to know the delta between them. What has happened to this model over time? What are the attributes we've added and removed? And therefore, if you can do that, you can detect whether changes are breaking or not. So are we going to be binary compatible if we do this upgrade on this model? How will our consumers and producers be impacted by that change? If you go as far as to register producers and consumers of your generated artifacts, you'll get data lineage or some form of data lineage out of the other end. As I mentioned before, you can do filtered views. You could do mappings between models. So like if you've got something that represents some communication, you could do a mapping between that and a physical model, for example. So and then co-generate the functions that go from one representation to another. And also you can compose models together, right, through imports. And then you can have a set of core models for your business that everyone uses, and then they can compose that together with other stuff that is pertinent to their particular line of business. So what you tend to get is like core models that everyone uses, and then stuff around the outside. But yeah, you can heavily compose them. What some of you may be thinking is like, well, okay, but wouldn't you just use like Avro, Prelibuf for these kind of things, right? Because they do a bit of code generation. And that's true. And I'd say like if you are using those things across your organization, you are doing a rudimentary form of model-driven development because we're agreeing a contract between producers and consumers of data. And that's really what's important. However, you're really only specifying the message types typically. That's what you're modeling, right? You're modeling, okay, I need to send this particular record to this system. So I will model that in Avro or whatever it is. I'll co-generate for that, and then between the two systems, and then we agree there's a contract. What I advocate for is that, a step further than that, where you can just model your whole domain, and your communications are a small part of that. If you're going down the Avro Protobuf Thrift route, like you'll typically have your message types, but then you'll probably be writing by hand transformations into your actual logical model or your physical model, right? So you tend to spend a lot of time doing that. You don't have the serialization problem, that's handled for you, so that's good. But equally, you are probably doing some form of translation between, representations of data. And this is like just to point out that like, we can't even agree in Scala, we can't even agree on how you serialize JSON, right? Just to point out that like standardize, yes, we have some standardization in terms of how we can model, messages and send them between each other. But actually, like even at a language level, in a programming language, you can't really agree on how you write JSON from an instance of a case class. It's really hard to define standards and to stick to them. And, it requires a lot of buy-in from developers and management in an organization to actually agree on, okay, this is the way we want to write our systems and for them to interact and have an opinionated architecture. So you have this problem within a single programming language, and then you explode that out, and you just got so many choices, right? As what you can do. So what can you do in Scala? Well, there's a little loved tool as part of SBT. So Eugene, the author of SBT, has wrote a little library called Contraband, which is a description language for record types and APIs, really. So that does code generation, and it does code generation for Scala and Java, and it would be pretty easy to write code generators on the Git repository now for like any other JVM language that you go to choose, Clojure, for example. It also generates a JSON codec, and it offers the ability to evolve your generated code over time in a binary compatible way. So I think it has the beginnings of actually quite a rich meta modeling tool. But I think it has potential to be extended a lot, which we'll get onto. So you can start off with how do you define a class? Well, it's all GraphQL style syntax, but with some additions. So you give it a package that that's self-explanatory. You got this sort of annotations or directives, as I was saying. In this case, we want our target is Scala. But equally, we could have a target Java. And our type is character, so that's going to result in a class of character with a name of string. The exclamation mark means it's required. So required field, it's not optional. And appears in, this is an enumeration. But this is also a list. So enumeration types, so episode. So you can see that I've got com example episode, and here I've got com example episode defined as an enumeration. So that should be fairly clear what's going on there. And then you got interfaces. So interface in Scala would result in a trait, and then your types can implement that trait, right? So it will just be something that's common among a bunch of things. You can also define operations, I think. And then also for compatibility purposes, you've got this since annotation where you say basically giving that will result in an extra constructor being generated. And then if you do have something with since, that means that it's always going to be optional, or you need to define a default. And in that way, it's not going to be a breaking change between one version of the code generation and the next. People won't be broken when they upgrade. Or we're sending data between systems with a newer version. Someone on the older version can still read it, right? So the generated code roughly looks like that. Eugene didn't use case classes by design. I actually think you could have got away with it. So that might be an extension to make. But yeah, so you got a couple of constructors there, and as you add attributes with since applied to them, then you'll get a load of more constructors added, default constructors, right? There's a whole bunch of other code that generates like hash code and equals and stuff as well. And then the JSON codec. So there'll be a bunch of sort of implicits generated, but basically you can create an instance of person in this case. And you convert that to JSON. You can print that. You'd be able to send that over the wire via, the web or whatever. And then at the other, you can take a string version of that, parse it into JSON, and then get back your instance of person. So, similar to like Proto or Avro, right? So you could have two individual services that agree on the model, code generate in Java and Scala, and then we can send and receive data between those two services if that's in JSON, and then we're guaranteed to have the same representation on the other side. There's no ambiguity. We haven't lost any data. We haven't had to write our own person object. person class with some serialization baked in, right, with all the assumptions that would involve. The contraband meta model is actually pretty nice. So, and it's not based on UML, so big win. So this is just a little part of it, and you can actually go into it on GitHub. It's actually, I'd recommend doing that if you want to understand really what a meta model is all about. So you got things like a record-like definition. So this is a trait, so there's implementations of this. But you got, so this is synonymous in a UML style meta model to a classifier. So what does a classifier? A classifier has a list of attributes. In this case, we call them fields. Okay, what's a field? Well, a field's got a name. It's got some type, whether that be a scalar type like string or date or whatever, or an actual a type we define ourselves. You can have default values. The directives are, so that since is a type of directive, right? So we say since this version. Directive is just the data structure around that. You can have different types of annotations, which are called directives. You might want to generate comments in your code. So typically in meta models, you'll see comments everywhere, like in every single piece of it, because you typically want to, you want to comment on the meta model itself, but also you want to comment on what you want comments in the generated code. Also, for things like operations, you might have arguments, and there'll be different types of arguments, like parameters. So typically in a meta model, we wouldn't disambiguate between return type of an operation, so a return type of a function and the parameters. They'd be contained within the same structure, but you just basically flag whether one's an input or an output. So yeah, that's kind of like what a very simple meta model might look like. So you got something that represents a class, something that represents a field. There'll be a different type of thing for enumeration. And then what you'll end up with when you write some text, and this parses that text, is a big tree. And basically the code generator, so the thing that this, that results in this, will take that big tree of your meta model and then basically convert it to text and it's as unglamorous as it sounds. So a code generator will typically have some sort of things that look like templates of text, but ultimately we're just writing strings to a file at the end of the day. They tend to be not particularly pleasant things to write. And, you can get away with template-based approaches some of the time, depending on what you're, for example, if you're generating a DDL generator, then you might get away with something like a template-based approach. But actually, most of the time, we're dealing with a tree of a meta model, and then recursing down that tree, and then you'll get code out the other end that hopefully looks and actually looks like this and compiles. So that's really why it's like that. That's why Eugene actually wrote this, like in SBT. It's like, I want to define this model right in a file, and then I want to build it straight. Like I want to code generate it and then build it all in one shot. Because the other problem is, you can define, if you have sophisticated meta models, you can define all sorts of junk in there that wouldn't compile. And you'd need some pretty stringent validation of your instances of your meta model. So that's not actually another big part of the process. So go back to the architecture. So actually, before you ingest a model into some kind of repository, you'd probably want to do a load of validation on it. And that validation would try to ascertain whether the resulting code from that model would actually make sense. So you're basically reverse engineering. This is what we want. Like this is what compiled code would look like, and these are the rules we want to apply to a model to make sure that you don't do anything dumb. Because obviously a meta model is a relatively free data structure, particularly if you're doing UML style meta modeling. and you can get a lot of stuff. You could put in a lot of stuff that doesn't make sense. So we need validation. Extensions. So if I didn't have a day job and I had infinite time, I think you could extend Contraband with new language mappings. I'd probably start with Python. That means you would probably take out SPT, and you just use the library part of it. Different serialization codecs, so Avro, Proto, Parquet, those kind of things could be added relatively easily. Generating physical data bindings from a logical model. So you could produce DB style case classes or Hibernate classes in Java, right? And with annotations similar in Python, so SQL Alchemy, sort of the record classes that it requires. Also physical file formats. So if you want to go from instances of classes to CSV, for example, you could have that capability. And then you can extend the model for different concepts. So you could have tagging, this thing represents, I don't know, a trade or a client or an account at a conceptual level, even though we call it something else. This is what it actually represents. Filtering of models, things like code lists are interesting. So code lists are like dynamic enumerations. So for example, currency lists are a good example of that. Currency lists do change more than you think. And typically if currencies are added or removed, that results in teams having to go in and fix their enumerations like mad. So having these dynamic things that you can populate at runtime that kind of operate like an enumeration but aren't an enumeration, they're quite useful from a modeling perspective. So there's lots you could do with a system like Contraband. That and these are all things that you aren't going to get in your sort of Avros or Protos and things like that. They're much more rich, and they're also things that you can't really get out of the box in the traditional case tool like Magic Draw, Erwin, and others. Nothing really exists in open source land that does this, what Contraband does plus what I've got here. And it would be kind of cool if someone could build it. And then we don't have to build it all from scratch at JP. So to conclude, model-driven engineering is, we're concerned with defining domain models and contracts between systems upfront, but then iterate on them. So it's not a formal method really, but before you cut code, think about how your application is going to interact with other systems and whether you agree on representations of things that you're going to send and receive. Right, so you don't want to be typing the same classes over and over again in different programming languages because you have a diverse tech stack, right? That's a waste, and you should be doing something about it, in my view. Also, it gives you the tools really to do better model evolution over time, so better evolution of your domain models, and not ending up in a hard place in terms of binary compatibility and things not working at runtime and stuff because you're not on the same version of a particular library. And then if you go the whole hog, register the fact that people are using a generated artifact as a producer or consumer, and what we'll end up with is something in between like business and technical data lineage, which is kind of the holy grail for a finance org. So you want to know where data has originated, right, who's producing it, and then who's consuming it at an attribute level, right? So we wouldn't capture the instances of what's being sent and received over the wire, but you would know at an attribute level who's consuming what. So yeah, that's really what it's all about in terms of what we're doing at JP. But there's like nothing really in here in this talk that you wouldn't find in like this book, very, very old book. It's just that we want to do this thing in a more modern way. We don't really need to start with UML diagrams. you can start with a very sort of basic textual language for defining a model, but then you can do some quite sophisticated things with it if you want to. So yeah, that's it. Any questions? I'm happy to take.